So today we're going to talk about the 16.3, the fundamental theorem for line integrals. And first of all, the first concept here is that of conservative vector fields. Okay, so a vector field is conservative if and only if these properties hold. But really what that means is that f is the gradient of some function f, some function little f, which means that basically f is the capital F is the partial of f with respect to x in the I direction plus the partial of f with respect to y in the j direction. So basically, but it's also, f is also p of xy, q of xy. So equating these, so those are equal and then those are equal to each other. Okay, so in other words, p is this partial of f with respect to x, and q is this partial of f with respect to y. So if you take the partial of p with respect to y, then you're going to get the mixed partial of f with respect to x and y. And if you take the partial of q with respect to x, then you're going to get a mixed partial. And so, so let me kind of officially do that. So I'm just doing what this is. This is going to be partial of f with respect to the second partial with respect to y, then with x, then y. And then here, this one is going to be the second partial of f with respect to y, then x. Okay, and so, and then these are equal to each other. You know, if you know if they can take these derivatives and everything, they're going to be equal to each other, except in some very weird cases. And so that's kind of where that goes. And then the fundamental theorem for line integrals is this: that if you have a conservative vector field, so by definition, so pretty much this the partial of, or the gradient of f, if you take the gradient, is going to be conservative. And the idea is that no matter, it's like, for example, if you go from one point to another point up in the air somewhere on the earth, then the amount of work that you take to get there is going to be the same no matter which path you choose, whether you go up and then over, or you go over then up. The amount of work that you do to take an object from one place to another is going to be the same. So that's what it means to be conservative. It doesn't matter which path you take. And basically, all you have to do is take the function at the end point minus the function at the beginning point, and that's going to be your integral. It doesn't matter what path you take. Okay? So this is at the end point of f at the end point minus f at the beginning point. Okay? So just to give you an outlook, so let's do some examples. So number one, a table of values given with continuous gradient is given. We want to find the integral of the gradient of f dot dr. That's this integral here, where C has these parametric equations. And so according to this theorem, according to that theorem, this is going to be f of the beginning point, of the end point, end point, minus f evaluated at the beginning point. And essentially, here's our r right here. Okay, so r of 1, if you plug a 1 into here, you're going to get 1 cubed plus 1. And for the x value, for the y value, you're going to get 1 cubed plus 1. And if you plug in a 0, for the x value, you're going to get 0 cubed plus 1. And for the y value, you're going to get 0 cubed plus 0. Okay. And so this is going to be f of 2 comma 2 minus f of 1 comma 0. And this value is right here. So there's 2 and 2. F of 2, 2, that's 6. And 1, when x is 1 and y is 0, that's this value here. So it's 6 minus 1. And so your answer for that one is going to be 5. Okay, let's look at number 2. Number 2 says determine whether or not f is a conservative vector field. If it is, find a function little f such that capital F is the gradient of f. If the field is not conservative, enter D and E. Okay, so here's our function right here. And let me point out that this first part is our P, and the second part is our Q. So P is all this, and Q is all this. And so once again, to see, just a quick check to see if it's conservative, you can take the partial of P with respect to Y, partial of Q with respect to X, and see if those are equal. And if they are, then it's going to be conservative. So let's go ahead and do that. Okay, so partial of P with respect to Y. So you're taking it with the partial of the first function with respect to the second variable. Okay, and that's going to be partial of this with respect to Y. So treat all x's as constants, and this will be just e to the x. And this is going to be cosine y. Okay, so that's e to the x plus cosine y. Meanwhile, over here, partial of q with respect to x, partial of this with respect to x is e to the x, derivative of e to the x is just e to the x. And then this one, treat cosine y as a constant, and you're just going to get cosine plus cosine y. Okay, and these indeed are equal. So that means it's conservative. And we go to the second part, which is to which is right here, find a function f. Okay, now that function, the partial with respect to x of that function is going to be the first, is going to be our p. So y e to the x plus sine y. Okay, now over to the right here, I'm going to say the partial of f with respect to y, partial of that same function f with respect to y is going to be this one, e to the x plus x cosine y. Now, if the partial of f with respect to x is all this, then that kind of boxes us in on our choices of what x could be, of what f could be. So you look for a function f whose partial is this, whose partial derivative with respect to x is this. And y e to the x fits the bill. If you take the partial of this with respect to x, you just get y e to the x. And for this one, x sine y works. If you take the partial of this with respect to x, then the x just goes away and you get sine y. Also, it's important to note, it doesn't come into play this problem, but a lot of times it does come into play that there could be a function in g in a function g of y that has all y's, that has no x's, and when you take the partial of this, it's just going to be 0 with respect to x. Okay, so this one right here gives you all that. Now, on the other hand, over here, you want to look for a function whose partial with respect to y is this function. And what does it is y e to the x, because the partial with respect to y is going to be e to the x. And this is x sine y. And then it's also important to note that you could have some function h in x. When you take the partial of this with respect to y, it's going to be 0. Okay, so all of this, so this gives you So this gives you all this. Now, the final step is to consolidate all this into one function. We know that the function has to be equal to this, but it also has to be equal to this. So the function that will actually that can equal both of those is just y e to the x plus x sine y. There's y e to the x, there's a y e to the x, there's a x sine y, there's a x sine y. We didn't need to have this part, so this will do for that one. Okay, number 3, the same kind of problem. So the first thing you're going to do is determine whether it's a vector field or not. And again, this is our P, and this part's our Q. So take the partial of P with respect to Y. And the derivative of cosine is negative sine, so this is going to be negative e to the x sine y. And then meanwhile over here, the partial of Q with respect to x, the derivative of e to the x is just e to the x, so you get e to the x sine y. Okay, now because this has a negative sign and this one doesn't, these are not equal. Okay, so that means that it's not a conservative vector field. And so the instructions are write D and E. So that would be the answer here. Does not exist. I don't know. That doesn't seem to make sense to me, but yeah, whatever. That's what you're supposed to do here. Just write D and E. Okay. So number 4. Part A, explain. Wait. Okay, so the figure shows the vector field f of xy equals 2xy plus, or 2xy comma x squared. And 3 curves that start at 1, 2. So it starts here at 1, 2. And each of these curves goes to 3, 2. Okay, so this curve goes this way, this curve goes underneath, this one kind of goes wavy along there. And part A is explain why this integral has the same value for all 3 curves, and what is the common value. Okay, so what you do is, this is our P, and notice that if you take the partial of P with respect to Y, that is 2x. And then this is our Q. And if you take the partial of Q with respect to X, you get 2x also. And so these are equal. And that means that it's conservative. That means this field is conservative field, which means that F is the gradient field. It's the gradient of a function little f. Okay, now let's go ahead and find that function, because we'll need to find out what that common value is. We'll need to use that function to find the common value. But we can answer the first question, part A. So the answer to part A, explain why, is the last selection, which is the vector field is conservative, and all 3 curves have the same initial and terminal point. Yeah. Okay, so here's the initial point. The initial point is 1, 2. And the terminal point is 3, 2. Okay, so let's go ahead and find the function f. So we know that f is the gradient of some function at little f. So we know that means that the partial of f of that little f with respect to x is going to be 2xy, and we also know that the partial of f with respect to y is going to be x squared. Is this the second one? Okay. So this information tells us that f is x squared y plus some function in y, possibly. This is what this information gives you. This piece gives you this, and then in general, you're going to pick up that. And then this right here is telling you that f has to be x squared y, because the partial of this with respect to y is just x squared. But you could have a function h of x. And so f has to be x squared y. It actually could be x squared y plus some other constant. Like you could add any number that you want, like you got 7 if you want, or whatever your favorite number is. I like to add 7s on there. And it's probably going to mark it right. Or you can add just whatever number you want. It doesn't matter, okay? But it doesn't help to add a number there either. So it's probably best to just leave it blank. Okay. So we found the gradient field, and now what you want to do is answer this second question: what is the common value? And so f dot dr, that line integral, is going to be our little f evaluated at the terminal point 3, 2 minus little f evaluated at the initial point. Okay, so this f evaluated at the endpoint, the terminal, minus evaluated at the beginning. Okay, so if you put in a 3 for x in here and a 2 for y, you get this. And then over here, do the same thing. Put a 1 for x, put a 1 for x and a 2 for y. This is 18 minus 2, which is 16. Okay, so 16 is going to be the answer. Okay, now let's go to number 5. Okay, so capital F of x, y, z, this is a function in x, y, and z this time. And C is a line segment from, it's a line segment from 1, 0, -1 to 4, 5, 3. So you have 3 variables. And there's not really an easy way to check whether this is a gradient function. So there's not really an easy way to check this, okay? Like there was when there's 3 variables, x, y, and z, okay? So, but we can, I mean, it's just as easy to try to come up with it, and then if it doesn't work, it doesn't work. Just try to calculate it directly, and then see if it works. So the question is capital F is the gradient of some function. And so in order for that to work, your f, the partial of f with respect to x, the first variable has to be this one right here, this yz. And the partial of f with respect to y has to be the second one, xc. Okay, so let me write that up here. And the partial of f with respect to z would have to be this last one. Okay, so this is telling you that, well, this is yz. xyz, the partial of f with respect to x is yz. Okay, but you could have a function in just y's and z's also, because when you take the partial of all of this with respect to x, you're going to get just this term. Okay, now over here, similar thing. xyz, partial of this with respect to y is just xz. But you could also have a function in x and z. And the partial of this with respect to y is just going to be 0. Over here, similarly, xyz, because the partial of this with respect to z is xy. But we also have this piece here, 2z squared. Partial of this with respect to z is 4z. And then you could have some function in x and y. Okay, now at this point, what we have to do is we have to reconcile all of this, because f has to be equal to that, f has to be equal to that, and f has to be equal to that. Okay, now a lot of students get confused because they see this piece right here, there's a 2z squared. There's not 2z squared here or here, but this 2z squared is actually, it fits here and it also fits in there. It fits in both of these spots here. This part of it does. Everything else is the same. Notice that that and that and that are the same. This piece fits in here, and it also fits in there. So our function xyz, f of xyz is going to be xyz plus 2z squared. Okay, now notice that another thing is I'm not tripling this up. Some people will write 3xyz. No, that's not how you're supposed to do it. This right here has to be able to be equal to this, and also equal to this, and equal to this, independent of, you know, the other two. Okay. So this is the easiest function that does it. And let's get to the evaluation part. Use part A to evaluate. Okay, now notice that it's going from here to here. So that means that this integral, and I forgot to write a little f right here, oops, .dr, is going to be little f evaluated at the terminal point, or 453, minus little f evaluated at the beginning point, or 1, 0, negative 1. Okay, so I plugged each of those into here. So 453 go into here. And then a 3 goes into there. Oops. That's the terminal point. Subtract. Ending point. Okay, 1, 0, negative 1 goes in here. That's times. And then negative 1 goes in here. Okay. 4 times 5 times 3, that's 60. This is 18. This is that's 0. And this is 2. So 76. Okay, so that would be that. So this is part B right here. Part A again is going to be this right here. XYZ plus 2z squared. Okay, number 6. Find the work done by the force field F in moving an object from P to Q. So here we have this force field, and they want to move an object from here to here. So the work Okay, so first of all, the work is going to be the integral, the line integral of f dot dr. And this is a conservative vector field. We won't get into that. We'll just say that it is. Well, we can get into it. If this is our P and that's our Q. I guess it doesn't take much to say partial of P with respect to Y is 0. Partial of Q with respect to X is also 0. Because there's no Y's in here, so it's 0. There's no X's in there, so that partial is 0. Okay. So the partial, what you want to do is f is equal to the gradient of some function f. And the partial of that little f with respect to x is going to be x cubed. And the partial of that little f with respect to y is going to be y cubed. Okay, so this means that f is going to be, okay, you want the partial to be with respect to x to be this, so x to the 4th plus 4 works. Okay, but you could have possibly have some function in g in y, a function in y, because when you take the partial of this with respect to x, you're going to get 0. Over here, y to the 4th over 4 fits, because when you take the partial of this with respect to y, you get a 4 coming down and the 4's cancel, and then this reduces by 1, you get y cubed, you get that. But you could also have some function in x. Okay, so here, this time, these terms are not the same. They're totally different, but you can reconcile it this way. This term is just this. And this term is just that. Okay, so these two end up being able to be equal to each other. X to the 4th over 4 plus y to the 4th over 4. Now, you can double check it. If you take the partial of this with respect to x, that goes away. This is x cubed. The partial of this with respect to y, this goes away. This is y cubed. So these both work, and we get these answers here when I take the gradient. So that means that the work is going to be f evaluated at the terminal point minus f evaluated at the initial point. Okay, so you put 2 into this function here. So that's 2 to the 4th over 4 for the x. You put this 2 in for y. That's 2 to the 4th over 4. Subtract. Put the 1 in for x here. That's 1 to the 4th over 4. 0 to the 4th over 4. 0 to the 4th over 4. This is 16 over 4. This is 16 over 4. That's 0. This is minus a 4th. Okay, so 16 is 16 is 32, minus 1 is 31. So 31 over 4